So now in this video we will be going through the step number 3, that is check for strength of the plate. Okay, in earlier videos we have gone through the connection problem, and in the last problem I can just recap. We have gone through the steps: strength calculations, design shear strength of plate in single shear, as well as design strength of the plate in the bearing strength. Okay, so we calculate VDSB and VDPB, and from that we calculated bolt value. So now the next step, that is the step number 3. So in step number 3, the first is design strength of the plate for rupture. This is according to the again clause number 6.3.1, page number 32. So here we got it, design strength due to yielding of gross section, which is the first criteria, and just before we to have this due to rupture, design strength due to rupture. This is for the plate, and it is given by the design strength and tension of a plate, that is denoted by TDN, as governed by the rupture of net cross-sectional area. So that value, net cross-sectional area AN at the holes, is given by TDN equals to 0.9 into AN FU divided by gamma M1. So what does this consist of? So gamma M1, which we already gone through, say table number 5. Okay, earlier videos we have just checked that. Then Fu is the ultimate stress of the material, and AN it is the net effective factor, net effective area of the member, which is given by this is how AN equals to B minus N D. Okay, so and there are some of the terms actually that won't be required in this case, and that multiplied by here T. So now if you just calculate this TdB, and that is equals to T and B divided by gamma MB, and that is 0.9 FUBAN divided by gamma MB. So that is the formula according to the higher score criteria. Now here we will be going through calculation of first of all AN. So AN we have seen that is equals to width of plate minus you have this D, that is actually, since n D is there, and that is multiplied by T, where n is the number of the bolt we do have. So width of the plate, say 120 minus 2 into this is 20, and this is multiplied by 16. So if you just calculate this part, so you will get it around 1280 mm square. So that's the AN, a calculation of AN in terms of mm square. Now we can calculate TDB accordingly. So TDB, this would be equals to 0.9. FUB, you got it, FUB earlier, that is 400, and FU for the plate, it is 410. Okay, though it is given FUB, but we need to consider it for the plate, and that is equals to 410 multiplied by 1280 and divided by 1.25, and this is equals to, so now if we just calculate it, so this value is coming out to be around 368.64 kilonewton. Now this has to be greater than the load value, so that load which is equals to 240 kilonewton, and therefore we can say this is okay. So that is safe in the rupture criteria. And then now the next part is to calculate design strength of the plate from yielding consideration. That is again from clause number 6.2, page number 32. So design strength due to yielding of cross section. So the design strength of members under axial tension, which is denoted by TDG as governed by the yielding of the cross section, and that is given by TDG equals to AG into Fy divided by gamma MO, and this is the values for it. Fy is the yield stress, Ag it is the gross area, and gamma MO, that is again partial safety factor, that is according to the table number 5. So if you just look at the table number 5 on the earlier page itself, so if you just look at this gamma MO, it is given here, and that is equals to, this is the gamma MO, resistance of members of to buckling gamma MO, and that is the value is 1.1. So now you can just go ahead with the calculation. So this is TDG, this is equals to AGFY divided by gamma MO. Now you need to calculate first of all your AG. So AG, as you see, this is the gross area, so that is equals to width multiplied by thickness of plate. So width is 120 multiplied by thickness of the plate, that is 16. So you can just here calculate, that is going out to be 1920 mm square. And therefore now you can calculate TDG is equal to 1920 into Fy, it is the yield stress, so that is equals to, in terms of steel, that is 250 divided by gamma MO 1.1 as per the table number 5. And if you just calculate this value, and in that case you will get around 436.36 kilonewton, and this has to be again greater than the load value, and that is equals to 240 kilonewton, and therefore you can say this is also okay, and this is again safe in terms of the yielding section. So this is not only safe against the rupture but also the safe against the yielding consideration, and therefore we can say the design is safe. Only check. So step number that is 4. So connection details. So it is, suppose this is the plate, we need to connect it like this, and we will have the bolt. So the thickness, it is a 16 mm thickness plate. This is 20 bolt, and then just draw it like this. So these are the two bolts, okay, and this is how the connection details can be. Okay, so in the next video we will be going through the next problem. Thank you so much. This is Dr. Srikant Arle. I will be guiding you about the problem related to the strength structure. Thank you.